Good afternoon, everyone. I'm Pratyusha Das, a fourth-year doctoral student at University of Southern California. Today, my presentation topic is symmetric subgraph spatio-temporal graph convolution and its application in complex activity recognition. In this presentation, first I'll talk about the preliminaries. Next, I'll move on to the proposed method, which includes spatio-temporal graph neural network for hand skeleton data, how we can decompose the hand graph, and then how we can use this decomposed hand graph for designing symmetric subgraph spatio-temporal graph neural network. Then I'll talk about the experimental results and conclusion. So in this presentation, our goal is to recognize dynamic hand action from hand skeleton data. And for that, we will be designing a stable model for hand activity recognition. In this task, complex activity analysis, instead of video, we are using hand skeleton data, because it has many advantages, like it preserves the privacy of the scene. We are not using any background information. It is very robust to sensor noise, and it is efficient in computation and storage. It is very easy to represent hand skeleton data using hand graphs, and this hand graphs has many interesting properties, and we will see them in the later of the presentation. So in literature, there are many kinds of action recognition algorithm for skeleton data, but there are very few literature on hand skeleton data. This spatio-temporal graph neural network was proposed for full body skeleton data action recognition. Then Garcia et al. Proposed first-person hand action benchmark dataset, which we will be using here. And they have showed some of the performance for hand activity recognition using some baseline algorithm and some of the existing algorithm in literature. Later, Lohit et al. Proposed this temporal convolutional network and temporal transformer network for hand activity recognition. But none of them proposed action recognition or hand action recognition algorithm using graph convolution. So in this paper, we will be proposing a graph convolutional network for hand skeleton data and how we can use the properties of the hand graph, which is this graph, for better implementation of the algorithm. So in this work, we are using this hand graph. This is symmetric and bipartite in nature. This is fixed, undirected. It has 21 nodes and 20 edges. So what is graph Fourier transform? Here we will be using some of this. So I'm just giving you a little bit preliminaries on graph Fourier transform. So once we have this graph G with vertex at V, adjacency matrix A, and degree matrix D, we can define the Laplacian matrix as a difference of this degree matrix and the adjacency matrix. And once we do the eigenvalue decomposition of this Laplacian matrix, the eigenvectors gives us the graph Fourier basis, and the corresponding eigenvalues gives us the graph frequencies. Next, I'll move on to our proposed method. So first, I'll talk about the spatio-temporal graph neural network. The Yan et al. Proposed the spatio-temporal graph neural network for full body skeleton data. In this paper, we are proposing spatio-temporal graph neural network for hand skeleton data. So as I mentioned before, we are using this hand graph. This is the spatial hand graph, and the spatio-temporal hand graph is designed, which is the lower figure. So basically in consecutive frames, we are connecting each joint, each hand joint, using a line graph in different time frame. So thus we design the spatio-temporal hand graph. Now, once we have the input data or input feature map, which is X in, it is a three-dimensional data. It has first number of channel, number of vertices, that is number of joints in the hand, and number of time frames. And for this spatio-temporal graph neural network, we do a convolution, a spatial convolution in its second dimension, that is in the vertex dimension, and a temporal convolution on its third dimension, that is on its temporal dimension. And thus, we compute the output feature map using this equation, where this AS is the spatial adjacency matrix, this W is the stacked weight vector of multiple output channel, and Q is the edge weight matrix for this edge of this graph. So this is a computation equation after each block of ST-GCN, and we will see for this work, we are using many layers of ST-GCN. We will talk about the final network later. So if a graph is symmetric and bipartite in nature, Liu and Ortega proposed that it can be decomposed to smaller graph with equivalent Laplacian matrix. And if we work with this smaller graph, the computation is much less complex and efficient. Our hand graph is also symmetric around this green finger, and we will use this property for decomposing the hand graph into smaller graph. So this is our initial hand graph. Once we decompose it into small first decomposition, as this is symmetric around this green finger, we get this smaller graph, two graph, but this GH minus is again symmetric in nature around this green finger, and the further decomposition is possible. And this is the final outcome. So we basically get four smaller graphs. As I mentioned before, this is equivalent by their Laplacian matrix. So the Laplacian matrix of the initial hand graph is L, and Laplacian of this hand graph is L phi. Then the relation between L phi and L is defined using this equation, where B is a Haar unit-based orthogonal matrix. And thus, if we want to filter a data using this Laplacian matrix L, it will be equivalent to filter the data using the Laplacian matrix L phi only if we pre-process the input data using this orthogonal matrix B. And as I mentioned, that number of operation is much lesser when we are using this L phi or the smaller graphs, and obviously it will be much efficient and less complex. So this is the pre-processing block. I'll just mention it here. As you can see, all of the, after pre-processing the input data, each of them are summation and differences of the input signal. And why it is important for us? Because if we, let's say if we are grabbing an object, the relative motion of the fingers are changing. But if we are taking an object from one place to another, the relative motion of the fingers are not changing, but the motion of the all fingers are same as the motion of the object. So this will be captured by the sum of the signal, which is this first one phi, and differences or the relative motion will be captured by this phi 2, phi 3, and phi 4. Now this phi 1 will be processed by this first graph, purple graph. This phi 2 goes will be used as input for G2, phi 3 for G3, and phi 4 for G4. And as I mentioned, that these are capturing different aspect of the input data, we will be using different temporal models for each of these smaller graph. And that's why we are using separate temporal models, and we have this separate weight matrix for each of the smaller graph, and we concatenate them, and at the end, after each layer, we compute the output feature map using this equation. So this is a complete block diagram. We have this input video, we extract the hand skeleton data, normalization is done, then we pre-process the data using that Haar unit-based orthogonal matrix. We used 3 layers of ST-GCN, and in each layer, we have these 4 smaller graphs, and each of them are using separate temporal kernel. At the end, we concat the features, we do a global pooling, softmax, and predict the action. Let's move on to the experimental details and the results. So I am using this FPHA dataset. It has 1175 data points. 6 different subjects are performing 45 action in 3 different scenarios. So we are basically considering all a lot of variation in the data, and they are interacting with 26 different objects. I have 2 experimental settings. In the first setting, I'm using different train test ratio. In the second setting, it's a cross-person setting. That means in the training set, I'm using the data of the 5 person, and in the test set, I'm using the data of the 6 person. So while training, the system did not see any data of the 6th person, so which is a more real life scenario. I'll just mention a little bit about Finger-ST-GCN, which is a baseline method. As I mentioned, that we are decomposing the hand graph by exploiting the symmetric and bipartite nature of the hand graph. But for different check, we were trying to see that if we use separate graph for each of the finger and use separate temporal kernel for each of them, how it performs. So that we named as Finger-ST-GCN. No pre-processing of the data was involved in this case. So this is my final results. So each of these 373 are means that how many layers of ST-GCN I have used, or so ST-GCN 3 means 3 layers of ST-GCN. And if you look at the last row, this is the proposed method, and we can see that this is achieving very good results or very good accuracy in cross-person setting, which is a real life scenario, and with many less number of layers compared to regular ST-GCN 7, and that is saying that it is with lesser complexity, I can achieve better accuracy. This is a comparison with all state-of-the-art algorithm. At the end, I'll just talk about the stability analysis. So this is cross-validation such stability, where I'm training the system with different sample of the data set and testing with a single test set. And so the accuracy of this test set should not vary a lot. If it varies a lot, the system is not stable. So lower the value of the variance of the test accuracy, better the stability. So lower this value of the psi, I get better stability. And we can see that ST-GCN 3 and S2 ST-GCN 3 are almost showing equivalent stability. And we are achieving much better stability than LSTM and also ST-GCN 7. And we are, as I mentioned in the last slide, that we are achieving better accuracy as well. So to conclude my work, we are proposing a hand skeleton-based spatio-temporal graph neural network. We decompose the hand graph, exploiting its interesting properties like bipartition and symmetry. And thus we designed this F-ST-GCN, which achieved better accuracy in complex hand activity recognition with a better stability in its model. Thank you.